Have you ever wondered what the actual shape of the universe is? Well, it turns out the key to unlocking that massive secret was hiding in plain sight for over 2,000 years inside a single controversial sentence in an ancient math book. Today, we're going to unpack how this one little line of text completely changed our understanding of everything. Yeah, this sentence right here. For millennia, the smartest people on the planet just stared at this thing, and they were all convinced this has to be a mistake, right? But here's the thing. It wasn't a mistake. Not even close. It was actually a clue, a breadcrumb trail leading to a reality far stranger and way, way bigger than anyone could have possibly imagined. So to get this, our story has to start way back, around 300 BC. We're talking about the Greek mathematician Euclid and his absolute masterpiece, a 13-book series called The Elements. Now, this wasn't just some book. For thousands of years, this was the book for mathematics. What made the Elements such a game-changer was how incredibly solid it was. Euclid built an entire system of geometry from the ground up, proving 465 separate theorems, all based on just a handful of simple, super obvious truths he called postulates. This whole approach became the gold standard for how you do math, period. And if you look at the first four postulates, they're almost insultingly obvious. You can draw a line between 2 points. Duh. You can extend a line forever. Okay, got it. You can draw a circle. Yep, all right angles are the same. Makes perfect sense, right? Everything's neat and tidy. But then came the fifth one. And here it is. I mean, just look at it. Compared to the others, this thing is an absolute monster. It's long, it's clunky, it's complicated, and it sounds less like a simple, self-evident truth and way more like something you should have to prove. And that awkwardness, that weird feeling, it just bugged mathematicians for centuries. So what did they do? Well, for the next 2,000 years, some of the greatest minds in history tried to prove this fifth postulate using only the first four. And you know what? Every single attempt ended in total failure. It was one of the most stubborn, frustrating problems in the history of math. So after 2 millennia of just hitting a wall, a new generation of mathematicians in the 19th century came up with a totally radical idea. They said, okay, what if we stop trying to prove the postulate is true, and instead, what if we just assume it's false? And you have to understand, this problem had literally broken people. There's this incredible story of a mathematician named Bolyai who practically begged his son Jonas not to work on it. He called it a bottomless night that would just extinguish all the joy in his life. But Jonas, he couldn't resist. And it's a good thing he didn't, because he was about to change everything. The plan was something called a proof by contradiction. You start by assuming the thing you're testing is false. So you say, okay, let's just pretend you can draw more than one parallel line through a point. Then you just follow the logic and wait for the math to break, for a contradiction, like 2 + 2 = 5 to pop up. But the absolutely wild thing was, the contradiction never came. Instead of finding a flaw, János Bolyai discovered something incredible. He found a completely new, perfectly consistent mathematical world. He wrote this triumphant letter to his father, and in it he declared, "Out of nothing, I have created a strange new universe." I mean, how awesome is that? And this strange new universe is what we now call hyperbolic geometry. It's a completely mind-bending reality built on a curved surface, kind of like a saddle or a Pringle chip. In this world, lines that look parallel actually curve away from each other. And if you draw a triangle, its angles always add up to less than 180 degrees. Totally weird, but it works. This discovery just blew the doors off everything. It meant that Euclid's geometry, the one we all learn in school, wasn't the only kind of geometry. It was just one option on the menu. Here's a really great way to think about it. Imagine geometry is a game. The first four postulates are the basic rules, how the pieces are allowed to move. But that fifth postulate, that's not a rule. That's you choosing the game board. Are we playing on a flat surface, like a chessboard, or is our playing field curved? And this table basically lays out the 3 main options. You've got your standard, flat, Euclidean world, where you get exactly one parallel line and triangles add up to 180 degrees. Then there's spherical geometry, like the surface of the Earth, where there are no parallel lines and triangle angles are more than 180. And then you have Bolyai's wild hyperbolic world where you can have infinite parallels and the angles are always less than 180. So for about 80 years, these non-Euclidean geometries were just fascinating curiosities for mathematicians. They were a cool what if. But then, in the early 20th century, a young patent clerk named Albert Einstein came along and realized this wasn't just a math game. This was the key to understanding gravity itself. Einstein's first big leap was to just throw out Newton's idea of gravity as this invisible force pulling things together. He realized that if you're in freefall, you feel completely weightless. It doesn't feel like a force is acting on you at all. So, if it's not a force, what is it? Well, Einstein proposed that massive objects don't pull on other objects. What they actually do is bend and warp the very fabric of spacetime around them. Mass literally tells spacetime how to curve. And that brings us to the final, brilliant piece of the puzzle. Objects like planets and satellites, they're not being pulled. They are simply trying to move in a straight line, but they're moving through a space-time that's been curved by a massive object, like our sun. They're just following the curve. And this straightest possible path on a curved surface has a special name. It's called a geodesic. This is exactly why astronauts on the International Space Station feel weightless. From their perspective, inside the station, they're just traveling in a perfectly straight line at a constant speed. It's only from our vantage point down here on the ground that their path looks like a curve around the Earth. So Einstein proved that space-time is curved locally, around planets and stars. But this just opens up an even bigger, more mind-blowing question. What's the overall shape of the entire universe? On the grandest of all scales, is our cosmos flat, like Euclid imagined? Is it closed, like a sphere? Or is it open and strange, like Bolyai's hyperbolic space? I mean, how could we possibly even know the answer to that? Well, believe it or not, the answer comes from measuring the angles of a triangle, but not just any triangle, the largest one we could possibly draw. We use the cosmic microwave background, the faint afterglow from the Big Bang, as our cosmic drawing board. By measuring the size of temperature fluctuations in this ancient light from different directions, we can form the corners of a universe-sized triangle. And using incredible tools like the Planck satellite, astronomers measured the angles of this cosmic triangle with breathtaking precision. The result? The curvature is pretty much zero. Within an unbelievably small margin of error, the verdict is in: our universe is perfectly, geometrically flat. Now, this flatness is incredibly delicate. If the average density of the universe were just a tiny bit more, like one single extra hydrogen atom per cubic meter, it would be a closed, spherical universe. One less, and it'd be open and hyperbolic. This leaves us with one final, profound question. Is this perfect balance just a cosmic coincidence, or does it hint at something much, much deeper?